Hi, good afternoon. Welcome back to the third session for the doubt clearing of week 3 lectures on aluminum based alloys and metal matrix composites. I am Ananya Nath. I am a PhD student in IIT Delhi. So let's start today's session. In week 3 lectures, mainly the dynamic strain aging was covered and also the precipitation hardening was started. Due to going into the dynamic strain aging, we need to be very careful and clear about the normal aging, natural aging and artificial aging. Only then we can understand the dynamic strain aging phenomena. And also it's a very complex and critical phenomena, so we have to be very clear about it. So if you have any doubt, Vanshika, you can ask, or else I'll start with my PPT.
Ma'am, actually, this lecture series is a bit complex to me, so can we go through everything once first, if it's
Yeah,
possible?
no problem, no problem. Okay, let me share my screen. Okay. So first, you had a doubt in last class, which is Berger vector. So I have prepared
Yes,
something for
ma'am.
that. So we'll start with the Berger vector first. So Berger vector, as I told you in the last class, Berger vector denotes that in which direction the dislocations will move. It basically is a factor by which the dislocation movement is defined, and for each type of dislocation the Berger vector, as it's a vector, so its magnitude and direction both matters, and both will be defined according to the type of dislocation. So we have two types of dislocations. One is edge dislocation, another one is screw dislocation. So apart from that, first of all, what is Berger vector? In this picture, you can see uh, these are the atoms. One, two, three, four. So these are the atoms. And if I start counting the atom, or if I make a loop in which I am just counting the atom in a particular direction, because also it's a vector along with magnitude, it will have a direction. So if I am going from this, then this and this, all the number of atoms are same. But for this lattice, as we can typically see that this is a distorted lattice, when we are going from this direction, the number of atoms is 5. Then in this direction, it's again 5. But in this direction, it's 4. In this direction, it's 5. This circles are atoms. So in this direction, it is 4. And in this direction, it's 5. So here is one extra, you can say. This distance will be the magnitude of the Berger vector, how much there is a shift in the lattice. So this shift is because of this extra half plane. Extra half plane is denoted by this symbol, like a perpendicular symbol. So due to this extra half plane, there is a mismatch in the lattice loop that we are creating here, or we are drawing. So this will be our Berger vector, which will have the magnitude of this much length and direction in this direction. In the direction we are counting, or we are making the loop. So it's basically the magnitude of Berger vector is the difference between the start and the end point. So if we are starting from this or this point, if we are starting from this point and we are ending like here, and this is one extra plane, or this is one extra magnitude between two lattice. This will be the magnitude of the Berger vector. And let's take another example, like for this is a screw dislocation. And in screw dislocation, in last class I have told you that it happens in the or it will follow a helical loop like thing to move inside the lattice. And this, the direction of the dislocation, or the direction how the dislocation, screw dislocation will move, is in this direction, right? And here if we count again the Berger vector, this is one extra atomic or say gap, which is denoting as the magnitude of the Berger vector. And it's again the direction is in this direction. So the lattice movement and the Berger vector movement here is similar, they are perpendicular. So in screw dislocation, the Berger vector and the dislocations are parallel. Sorry. Parallel, not perpendicular. I have drawn the sign of parallel and saying perpendicular. It's parallel. So the Berger vector direction is this, and the lattice movement is also in this direction, or the dislocation movement will be in this direction. So they are parallel. But at the same time, for edge dislocation, here you can see for this extra half plane, there is edge dislocation, extra half edge, and this extra half plane is in this direction. But the Berger vector was in this direction, and the magnitude is this much between the end point and the starting point. So they both are perpendicular. So for edge dislocation, it's perpendicular. So this is a very simple thing, not much complicated. And as we are stressing upon the dislocations much more in this session, so it's just a brief overview about the Berger vector. So apart Berger vector, I have also added something about slip plane. So what is slip plane? There are number of planes in each lattice. Lattice means they can be FCC or BCC, face centered or body centered, or simple cubic or HCP, hexagonal. So there are a lot of planes, particularly for typically or particularly for few number of planes. You can see those are always tend to have the dislocations in those planes. So in FCC atom or FCC lattice, this is the plane 111, which has the tendency to have the dislocations along this particular plane. So in FCC there are 12 slip planes. In BCC there are lot more number of slip planes, though that is a closed packed structure. So slip planes cannot allow the dislocations to move very fast in them, but FCC can. So that is why FCC structures are ductile in nature, but BCC structure are mostly brittle in nature. And this slip plane will have a direction in which they will allow the dislocations to move, and that direction is called the slip direction. And the slip plane plus the slip direction makes the slip system, is very important. So this is about slip plane. It was also related to the dislocation, that's why I have added. So here you can see for BCC, FCC and HCP, there are number of slip planes. Although the active slip plane means there are slip planes through which or along which the dislocations will move. But until unless you apply some external stress, force or strain or temperature in that lattice, the slip planes will not allow the dislocations to move, or the slip planes will not move. So what happens is in FCC the number of active slip planes are more than BCC. Active means whenever you apply some temperature or external force along those active slip planes only the dislocations will start moving. After that, the other slip planes will allow the dislocations to move, and that active slip planes numbers are more in FCC. That's why FCC is ductile in nature, because ductility is more like if we are applying some external forces, the lattice material will have some dislocation movements inside it, which will result in the percentage elongation in the material, and the material will not be broken. But for brittle material, when we apply some stress or tensile stress, it easily gets broken. So that is the difference in brittlity and ductility. And due to this more number of active slip planes in FCC, it allows the ductility to be more and the dislocation movements more in number in dislocation movements and these things. So after that, there is big three topics. So mainly, as I said, aging
Excuse me,
is
ma'am.
yes, yes.
Ma'am, actually, one thing, like we can then assume that all FCC materials will be very ductile and very little hard, like they will be rather soft.
Yeah, you can assume that ductility will come with the FCC lattice.
Oh, okay, ma'am. And ma'am, how about HCP? Like HCP is also like this.
Yeah, HCP is also having the slip planes, but HCP is having less number of slip systems. So obviously, its ductility will not be that much.
Ma'am, I didn't get like you said that slip system is like a combination of slip plane and
Yeah, yeah.
slip
So
direction.
yeah,
So,
so number of slip planes mean ductility is more.
yeah.
So
Uh,
HCP is having less number of slip planes or slip systems, means the ductility in HCP is lesser than HCP or
okay, ma'am.
FCC, sorry.
Understood.
Yeah. So next we'll start with the topics of big three. First, we need to understand the part aging. So I'll ask you that what did you understand by aging? Then only we can go to the dynamic strain aging.
Ma'am, actually, like what I got was that in aging, you are trying to apply some load on the material, then you unload it, and then you keep it for some time, and then reload it. So basically, the changes that in the yield point and other points will be seen. There will be some changes due to this aging.
So what happens is, if this is the straight curve, uh, up to this point, the material obeys Hooke's law. After this point, it can retain its shape and original size after removal of the external applied force, but it will not obey the Hooke's law. And beyond that point, it will start showing the plastic deformation. So there the upper yield point comes, then lower yield point, then it will go up to the fracture point. This is the typically drawn stress strain curve, right? So there when upper yield point and lower yield point comes. So upper yield point signifies something and lower yield point signifies something. So do you know what they signify or what they denote?
Like ma'am, in case of that solute theory, like that we did in the last class, the upper yield point will say that the solute atoms are following the dislocation and pinning them down correctly, but after a particular time, that process is not that good.
Hmm.
So I think it's if
Yeah, yeah.
it's
So
with
it's
that theory.
absolutely right. So upper yield point means you can see from here the stress is increased. Strain is always increasing, but when the upper yield point is there, it will start decreasing. Means the solute atoms has locked the dislocations or pinned down the dislocations. So basically, if this is the dislocation, in simple layman term, if you want to understand, if this is a dislocations moving in this direction, and there are some solute atoms, so they have come to this point, they have gathered together, they have made some precipitations or atmosphere or cluster, due to which the dislocations cannot move farther. So this is the upper yield point. The solute atoms have locked the dislocations at that point. After, even after that, if we still increasing the strain, it will get more energy to overcome this barrier of solute atoms. It will overcome the barrier, and it will again start moving the dislocation. So at that time, this lower yield point comes, when from this point the dislocations only move, they do not stop until unless they meet the fracture point. Means in ductile material, if we are going for any tensile test, so at this position, if we are just applying some tensile force onto it, some strain is increasing with time. So always remember, we apply the strain in the material, which results in the stress inside the material. So that's why the strain is in x-axis and the stress is in y-axis. These questions are often asked in many interviews also. So
Yeah.
anyway, when we apply the strain at the middle portion, the stress will be more, the stress concentration will be more, and due to which after certain time there will be a cup and cone type shape, which denotes the ductile fracture. Hmm? So this is what happens in the tensile test, and this phenomena, this situation is what we are dealing with here. So what happens in lower yield point? So the stress start increasing only. So in aging, what happens is, this is dislocation line, so I'll talk about it. Before that, what happens is, when we load it and then we unload it, so when we have unloaded, after that, if we are holding the material at a particular temperature, at an elevated temperature, or even at room temperature, what has been observed is the solute atoms still try to move and try to catch up the dislocations, and after some time they really catch up the dislocations. They sit in front of the dislocations and the dislocation movement is hampered. That is what the result of the aging, normal aging, which is a natural aging or artificial aging. So in artificial aging, what happens is, when we are holding this material after unloading, we are holding the material at an elevated temperature. This elevated temperature gives an external motivation to the solute atoms to further move and catch up the dislocations. So for elevated temperature aging or artificial aging, the solute atoms feel easy to move and catch up the dislocations. So aging is also a type of precipitation hardening. But then if we are reloading it, in stress strain curve, we'll see a yield point reappear. After this yield point also, when we have unloaded it and then we are loading it, this lower yield point again reappear, or due to which the dislocations move, uh, get that energy to overcome the barrier of the solid atoms, precipitations or the atmospheres, and they will not pin down again. They will start moving and moving until unless they meet the fracture point in the straight strain curve.
Excuse me, ma'am.
Yes.
Ma'am, I have a doubt here. Like, when you are saying that we are loading it and then unloading it, so we are waiting till the yield point to come, and then, like, when you get the upper yield point, you have stopped the job, and then after that,
No,
you're
no,
going
no,
to.
no, no, no. When we have loaded it, right?
Yes.
Here, we have loaded it and we have unloaded it. If this is a force and this is a time, So for some time we have loaded it and then we have unloaded it. In stress strain curve, what happens is, for, apart just forgot about the say stress strain curve. We have loaded and unloaded, and at that unloaded situation, we are just holding the material. We have kept the material in our sample box for months or for days, and then we are going for any tensile testing. So what we will see is the hardness has been increased. Suppose we
Mom,
have two samples.
ma'am,
I am just trying to
okay,
clear it out. We have two samples, right? One sample I have loaded like up to A point. Second sample also I have loaded up to A point. A is some value of the force I am giving. Okay. Then we have unloaded it to the original point. Means there is no loading. We have unloaded it, and after unloading I am going for the tensile testing. Okay. I am going for the tensile testing, and for sample 2 I am keeping this material in my sample box, and after 40 days I am going for a tensile testing. So what I'll see is, in tensile testing, I am having or I am getting one result, and after 40 days when I am doing the tensile testing of the sample 2, which was the same sample, samely loaded and samely unloaded, but I have kept it for 40 days at room temperature in my sample box, the result I am getting after tensile testing is different. So what I'll get is, I am supposed to get more hardness in case of sample 2. So this more hardness is the result of the natural aging process. And aging is all about precipitations of the solute atoms, or even if the attraction between solute atoms are not that much, so the solute atoms will make an atmosphere or clusters. So due to which the dislocation movement has been pinned down, and due to which the hardness has been increased, and this is what I am getting after the result. So do you understand this much?
Yes, ma'am. Ma'am, actually, I went through the last week's lectures also, like week 4. Ma'am, in that we are talking about this hardening, like precipitation
Yes.
hardening. You said they're similar, so like in that, sir was discussing that you have to take the alloy to a single phase region, like you have to heat it first. So here we're not doing that.
No,
How?
it's natural aging. That comes under the artificial aging. In precipitation hardening also, you can do the precipitation hardening in various ways. Go don't Right now, don't go to the that part. When you'll understand this natural aging and dynamic strain aging, then you'll understand the difference between these all things. Hmm? Because
Okay, ma'am.
this is already very complex. So this is
Yes, ma'am.
natural aging. So the number of solute atoms to be precipitated, or do not consider it as a precipitation, even the number of solute clusters or atmosphere will not be in that much. Like if we are doing or keeping the material at elevated temperature, but still the number of atmosphere will be more than sample 1. This is why we are getting more hardness in sample 2. So this can be
Yes,
counted
ma'am.
under the natural aging process. So aging is two important things. One is, aging means the solute atoms are restricting the dislocation movement, and due to which the hardness is increased. So do you understand why these solute atoms are restricting or the solute atoms are restricting the movement of the dislocation, and the hardness is increased? What is the reason behind it?
Like the velocity of as the velocity of the dislocation increases, like this the stress between these dislocation, it increases. So these dislocations find it difficult to move. So that's what is happening, right?
Okay, so there's a simple thing. If we have a simple example of ductility, is a rubber band. So if you have a rubber band of this much length, if you are pulling it from both the sides, it can be maximum of this length. But beyond this, if we are still just pulling it, it will break. But if you have a long hair band, you if you are pulling it, it can be of more length, result in more percentage elongation, and that's what happens in inside the lattice, inside the material. So when there is restriction in the dislocation, so this dislocations are type of rubber bands. So if these dislocations can move, so they can allow the material to get stretched when they are under this pulling force or tensile force. But if these solute atoms are restricting the movement of the dislocations, so these dislocations cannot move further. So even then we are pulling this material or giving or applying some tensile force, this material will not be allowed to get more percentage elongation, as these dislocations cannot move. These dislocations are the main thing which gives the percentage elongation. So if this material is having very less dislocation, and if you are pulling it, so it cannot have a much more percentage elongation. But if this material is having a lot number of dislocations and they are free to move, the percentage elongation will be much more, which is a simple thing. So this is how you can think of now about the solute atoms and the dislocations. Why we are trying to restrict the the dislocation movement. So at the end of the dynamic strain aging, you will see that this dynamic strain aging basically reduce the ductility. Ductility means how much percentage elongation a material can sustain, or how much
Yes,
percentage
ma'am.
elongation the material can result in. That is all about ductility. So that percentage elongation comes with the dislocation movement. So this is why we are restricting the dislocation movement by applying something externally, so that the solute atoms can restrict the dislocations. So this is the basic of this ductility. So after that, this aging comes into the picture. So aging means we are doing something with the material, so that we are not even applying any load or anything externally, but still we are restricting the movement. We are just loading it, unloading it, and keeping it for an elevated temperature or room temperature, and aging is happening. And after aging, when you are reloading it, at the time of reloading, the ill point reappear. Not at the time of aging. After aging, the ill point is reappearing due to that solute atoms. So you just think, if the aging was not there, okay, aging is not there, so you are loading it and loading it, you are not unloading and keeping the material. So if you are only loading it, with the strain, the stress will always increase. But as you are unloading it in between, so the aging is taking place. And also as you are keeping the material for few days or months or even few hours. So in the dynamic strain aging, what happens is, mm,
Excuse me,
yes,
ma'am.
yes, yes.
Ma'am, that is the reason why there is a dip in the strain because we are aging it. Uh,
Which one?
like the reason why there's a dip in the strain, in the stress strain curve is because we are aging it.
No, no, no.
Uh,
When we are loading it now, in normal graph also, you'll
yeah,
see there is a this one high yield point and
yes,
low yield point.
yes, ma'am.
So this also appears due to not aging, but that is due to the normal material,
So about this dislocation interaction.
yeah, dislocation and solute atom interaction. But this lower yield point, why it happens is because of that restriction, and then it is free to move these things.
Okay, ma'am. I get it.
So yeah, so now the aging part is done. So now we'll move on to the dynamic strain aging. So this was one part where there are three types of sedation also. We'll come to that point. So there are loading, then unloading. After unloading, we are aging. We are just keeping the material for some time, and then we are reloading. And at the time of reloading, this yield point reappear. But if this happens that at the time of deformation only, or at the time of loading only, the yield point reappear, that is called the dynamic strain aging. What happens in the normal stress strain curve? So the normal stress strain curve is different for different material. Although we have learned this type of curve for any ductile material, but it's not true. You can see, right? For steel it's different, for aluminium it's different. So for aluminium we are talking about. So for aluminium during deformation this reappear, and this can be like this also. This can be like here serration and then fracture. This can be like only for few intervals this, or this will go out. So different types of curves we see for aluminium due to this dynamic strain aging. So for dynamic strain aging, what happens, before going into that part, another important thing is there are two concepts. One is strain, one is strain rate. Strain is nothing but you can visualize, we are just pulling the material, we are just applying the load. That is what that is how we are applying the strain. But strain rate is with per unit time, per unit second, or per unit time, how much strain we are giving, how much strain we are applying. So strain rate is also very important thing here, because you will see in dynamic strain aging what happens is, due to the strain rate increase, there will be some temperature increase inside the material, which also gives the solute atoms an activation force or motivation to go and lock the dislocations. So normally what happens is, with strain or with strain rate increase, the stress increases up to this point, and then we are getting this dent and then fracture point. So this dent, or why we are getting this lower yield point, is because of the dynamic strain aging. This is why that was taught like dynamic strain aging, very common phenomena for all type of material. We can avoid the dynamic strain aging by different means. But before that, just see what happens. So normally when we apply the strain rate, when we increase the strain rate, the stress increases. How? This curve is giving us the result. But in dynamic strain aging, what happens is, after some time, the dislocations moving and solute atom is also moving, but as the strain rate is increasing, some temperature increase inside the material occurs, and due to which the solute atoms get that thermal activation or activation energy to move very faster and sit in front of the dislocation, and at that time the stress reduces. So this is DSA and this is no DSA. So is it clear?
Yes, ma'am.
So it's very simple. So there are a lot of theories covered in this weak lecture. That's why you felt it tough or complex, but it's not that much tough. So it's like we are applying the strain rate, and we are applying the strain rate means we are pulling the material and we are increasing this pull force with time. So obviously the temperature will be increased inside the material, and due to which the strain rate is increased and the stress is decreased, because stress is what? To restrict the percentage elongation or to restrict the material flow inside the lattice, the material is giving a resistance force, and that resistance force is stress what the material experience under loading, and that resistance force the material is giving by the means of solid atom movement. And as the solid atoms has already pinned down the dislocation, so the obviously the stress will be decreased. And even after some times we are still increasing the strain rate, the solid atoms cannot have that much energy to sit over there or to restrict the dislocations, because at the same time dislocations will also get that thermal activation, and after some time they will again uh, overcome the barrier of the solid and move forward. So this is what happens, how the lower yield point again reappear, and the curve looks like this. Is it okay?
Yes, ma'am.
So now you can understand what is the strain rate sensitivity. So now we'll go with the lecture things one by one. Before that, I need to add slides. So yeah, the first thing was dynamic strain aging. As I said, for plain carbon steel from 225 to 375 degree centigrade, this dynamic strain aging occurs. So obviously dynamic strain aging is not a normal phenomena. It is obvious, but it still it still needs a situation and a particular combination of situations to occur, like a particular range of strain rate and a particular range of temperature, beyond which limit the dynamic strain aging will not occur. It's obvious because dynamic strain aging is a different phenomena than the normal phenomena of load, unloading and aging. So obviously in carbon steel there is a temperature range. For aluminium it can occur in room temperature. Also we have learned that for aluminium this can occur for magnesium atoms. So what does it mean is, for the magnesium solutes the dynamic strain aging can occur. So if we are applying that 10 to the power minus 5 to 10 to the power minus 2 per second strain rate, we have increased the strain rate in such a way that our strain rate is falling in that range. Even at room temperature, the magnesium atoms will have that velocity to move faster and sit down in front of the dislocations, so that they can pin down the dislocations. So this is what means by these lines. Next, there is sedation. So sedation means wahi ki there is a dent in the stress strain curve, and this dent can appear and disappear. So what happens is, in sedation this dynamic strain aging occurs at a particular temperature and a particular strain rate. So in dynamic strain aging, the solute atoms is or are locking the dislocations. It can happen that because of that high strain rate, so for high strain rate what happens is, we are applying strain with time, with a unit time we are increasing the strain very faster. So at that time what happens is, the dislocations don't get enough time to move inside the lattice. But even or if they somehow get they somehow move inside the lattice, this type of sedation occurs, means the solute atom is restricting the dislocation movement, but again the dislocation is trying to move, and again the solute atom also has that high energy due to the high strain rate, and again this happens for longer duration. Then this sedation flow or sedative flow or sedated flow occurs in the straight strain diagram, which looks like this. After some point, this solute atoms will not be able to log the dislocations, because the dislocations will get that much high thermal activation to move farther and very faster, so that the solute atoms cannot log them or catch them up. So from that point it will go up to the fracture point. So this is what meant by this sedation. Also there is a tensile sample using which we go with the tensile test. So at this gauge length only this sedated flow occurs, and due to which the surface roughness also hampered, because solute atoms are making clusters and they are sitting over a position. Again they are making some another cluster to lock the dislocations, and this moves, and this happens in the gauge length, and as the solute atoms are making clustering, or they are making atmosphere, so due to which the surface roughness of this gauge length is hampered, and we can see visualize the surface roughness in the gauge length. So this is what meant by sedated flow or sedation. Also we learned about the this sedation was also described by Porterin La Chatelier scientists, due to which it's called PLC effect as well. So PLC effect is nothing but the same thing. We are just increasing the strain rate, and this sedation flow we are getting due to the stress increase and decrease, and also the increase and decrease in stress giving us the magnitude of this sedated flow or delta sigma. This magnitude will be dependent upon the temperature which is increased inside the material due to the strain rate increase. So this will depend upon strain rate and temperature as well. Now there was another topic of waiting time. So as I said, the dislocations are right now trying to overcome this barrier. The time they are taking to overcome this barrier is nothing but called waiting time, TW. They are waiting in front of the dislocations to just overcome this. There was a thermal activation function and graph. So if this much total energy is needed to overcome the barrier, so this much is thermal activation and this much is applied stress. So you can say also, due to this much applied stress, the thermal activation will be the result. So even if you didn't apply any external temperature, you didn't increase any external temperature, due to the externally applied force, there will be some increase in the temperature which will result in this all over thermal activation energy, which is needed for the dislocation to overcome the solute atoms or the barrier of the atmosphere. So this was easy. And also if there is no DSA, or if there is no dynamic strain AG, what happens is, with the increase in strain energy or strain rate, the waiting time decreases. Means these solute atoms are not there to restrict the dislocation movement. The dislocations are just moving forward with a high speed with higher strain rate. But as soon as the DSA occurs, the solute atoms are positioning over here and the waiting time increases. So that is also one thing, the difference between normal stress strain and sedated stress strain curve. In lecture 2, it was taught about the sedation only, or the DSA. So for different strain rate, the curve was shown like this. For this same strain rate, the stress is low. If we are increasing the strain rate, the stress is increased, but here for same strain rate, the stress has been decreased. So this is the difference between no DSA and DSA. So for DSA, the thermal activation needed is less because already for the increase in strain rate, the strain rate is increasing, and as a result, the temperature inside the material also increases, which helps in getting this thermal activation, which is also needed for the solute atoms. So we also know for aluminium the solute atoms sit in the substitutional position. So in substitutional position, they need to first find a vacant position to jump into. So if this is a solute atom, they first need to find out which is the nearest vacancy they can sit into or jump into. They will jump there, and then again they will find for the next vacancy. If this is the next vacancy, they will jump here, and this is why they take more energy, or they take more time to jump into different positions or to move. Whereas also there is a reason why in steel the iron atom is smaller, and the but the alloying element, which is like carbon, nitrogen, those are even smaller. So for in case of steel, between the iron atoms, this carbon or nitrogen can sit in the interstitial position as these are so smaller. But for aluminium, the alloying elements are magnesium, copper, manganese, zinc, which are of same size like aluminium or some higher than aluminium. So that is why they cannot sit in the substitution position, or sorry, they cannot sit in the interstitial position. So this is why they always sit in the substitution position. And you can imagine some solute atoms, if they are sitting in the interstitial position, it will be always vacant. The interstitial positions are always vacant, so they can move very easily. But for substitutional atoms, they cannot move very easily. They first need to find out what is the vacant position in the nearby, then they need to jump. Always they are jumping from one bonded vacancy to the another bonded vacancy. This is why they need more activation energy to jump into. This is why in aluminium the solute atom movement is slower, and the strain rate increase is giving that much high energy or temperature increase, which helps the solute atoms to move faster, finding the vacant positions faster and jump into. So this is the DSA. Then the peening theory. So the peening theory is telling us the similar thing, like if this is a straight strain curve, and if we are increasing the strain rate in this direction, if we and the stress is increased, so when we are loading, so the stress is increased. After some time, the stress will decrease, and again after having the yield point, the stress will again increase unless until they find the rupture point. So when the solute atoms are at A position, so I am using the same notations used in the lecture as well. There was a formula which was giving us the stress distribution in terms of the strain rate, right? This one. So this equation we were just differentiating, and the result was something like this. I'm not doing the differentiation. So this was giving us the result like this double dot epsilon, which is the first order differentiation of the strain rate, is giving us infinite value at point A and B, because those are the maximum and the minimum point, and in differentiation the maximum minimum points give us the infinite value. So because of which this was concluded, like if the strain rate is this much, the material is at this position, due to the infinite result, it will suddenly jump to this position. At this time they are supposed to be at this strain rate, and this sigma or stress value, they are having this much strain rate, which is so high. So the material is experiencing so much high strain rate at the same level of stress, when they are supposed to be at this position, the strain rate we are applying. So again, when we increase the strain rate to this position B, so at C, the strain rate is supposed to be this much and stress is supposed to be this much. But at C, the material is having this much stress. So what happens is, if we increase the stress, if we increase the strain rate up to this B point, again that is a minimum point. So the result will be infinite again. So there will be again a sudden jump into point D, and uh, which result in the minimum stress again. So this is a loop. We are increasing the strain rate and we are getting a loop in the stress value. The stress is, sometimes the stress is increasing, sometimes the stress is decreasing with the increasing strain rate.
Excuse me, ma'am.
Yes.
Ma'am, I have two doubts here.
Yeah.
Firstly, ma'am, how is this seen in the material itself? Like, when you're actually doing it, how does it look like? Is it like really fast that you can't even make out, or
No, no. From outside, you can't see these things. But
okay,
inside, if you go for any microstructure analysis with a real-time monitoring, suppose we are just increasing the strain rate and we are having a real-time monitoring. So at that time you can see, if you can see the dislocations that much dimension, then only you can see these things. Otherwise you can't see these things. Means you can just have the theoretical part,
okay, ma'am.
but
Also,
these are some
yes.
experimental results which are already published. That's why we got to know about these things.
Okay, ma'am. And ma'am, also, is this like an SHM sort of a thing?
Not simple harmonic motion, but you can
Uh,
imagine a loop, like the, you can say it's a simple harmonic motion like this, but not that much constant. The motion is not that much constant. It will be just uh, ununiform or
yeah.
non-uniform. The uniformity will not be that much key, you can say SHM.
Yes, ma'am. Ma'am, also, like, where does this end?
Sorry.
Where does this end? Like, how it
Okay,
just
where does
continues?
this end is when the temperature range is crossed. There is a particular temperature range and the strain rate range in which this sedation happens. The DSA
Okay.
happens. So
Yeah, ma'am.
when
Yeah.
the temperature range or the strain rate range is crossed, this will end and this will go up to the rupture point.
Yes, ma'am. Understood.
Yeah. So that is why, so this was all about the DSA, and this is the pinning theory. Pinning theory means the, like, like here the solute atoms has seated and locked the dislocations. So that's why this point we are having, but the strain rate is increased at the same stress value. Again, when we apply or increase the strain rate, the stress is decreased. So the strain rate was supposed to increase, but the stress is decreased. So this decrease is because of that pinning down the dislocations. So this is the sedation. and due to this loop only, that surface roughness we get generally. So this was up to the peening theory. So this is what we can say, or due to which we are getting the negative strain rate sensitivity. So strain rate, generally when we apply more strain rate or increase the strain rate, the stress increases. But here at a particular strain rate interval, we are getting less stress. So due to which there was a thing like these points are the lower strain rate and upper strain rate, and if you are working in this range, this serration or serrated flow will occur, will be appeared. And in this region only we are getting this negative strain rate sensitivity. So which is nothing like just when we are increasing the strain rate, the stress is decreased. This is DSA. Beyond this range, here and here, you will always get this type of phenomena. No DSA. So this is what was meant in the up to lecture 3, I think, or lecture 2. After that, there were types of serrated flow or types of DSA. So it's nothing like if you are dealing with the material in that particular strain rate or a particular temperature or combination of both, this strain rate can occur in different types. Like the band which is appeared in the surface roughness in the gauge length is called the leader band also. That band, if it's propagating throughout the material continuously, then we get the type A. So I have
Ma'am, could you please spell it?
it's LIDAR. I think the spelling is this LUDER, but I need to recheck.
Okay,
You can recheck.
sure,
It's
ma'am.
called leader. So leader band. So depending upon how the leader band we are getting, so there are type A, B, C, D, E, up to E, but here only A, B, C is discussed. So we'll see. So in A, it's continuous movement of the serrative flow inside the material. So continuous movement means the solute atom is restricting the movement. Again, the dislocation is trying to move. It has moved some length, but again the solute atoms has restricted the dislocations. This type of things. This is why the movement is somewhat like this. This, then again, then again. Continuous movement. In type B, this is like this, you can see here. So what happens is the serrative flow or the dislocations are again and again coming. The dislocation sorry, the solute atoms atmosphere is again and again coming. They are getting the positions to be seated at a very adjacent positions. So this is why the serration is coming very fast. Distinct serration is coming like not throughout the band, but at a particular length only. It's not propagating throughout the band, but at the particular length of the leader band this serration is happening. But in C there is no propagation of the serration. This thing will be demolished after some time in type C. So
Ma'am, can you please explain B
yeah,
once
so
again?
so yeah, so what happens is in type A, so in type A, if this is the gauge length where the serration is happening, this was the first distance or first position where the serration happened. If this is L1, suppose, so in type A, so what happens is in L1 only the serration is happening, and it's happening like very fast. The serration means the solute atoms is again and again getting the adjacent positions to be seated very faster, and the dislocations cannot move likely, like they are trying to move and they have moved a very little bit, but again the solute atoms have seated in the adjacent position, and again this serration is happening. The dislocation is trying to move in this direction, but the solute atom has again seated in this position. Again the dislocation is trying to move in this direction or somewhat in other direction. The solute has again seated in that position, and due to which in that small gauge length only a lot of serration has been occurred, and over the full tensile sample only this much will have the rough surface, which indicates the serrated flow. This is type B. For type A, first that was L1, but with time this LIDAR band is propagating throughout the gauge length, and now we are getting an all over surface roughness in the whole gauge length, and that surface roughness is average. Here the surface roughness is very high and it's restricted in one position, but here the serration or serrated flow has been propagated in throughout the gauge length. It is L2, which is obviously greater than L1, and the surface roughness is average. This is what happens in type A, a continuous propagation inside the band, leader band, the continuous propagation of the leader band. In type C, what happens is there is no such propagation, that the serrated flow was started in this position first in L1, and the grains has been nucleated, means nucleation means the small grain is resulted in larger grain. So larger grain means the ductility has been increased. So the dislocations has found some path to move and overcome the solute. So the serration is very minimum, and after that it demolished. So the surface roughness will be lower in that case. I am drawing very badly, but okay. The surface roughness is in this much length only, which is L2, but L2 is greater than L1 but not that much. Here many greater than L1, but here not that much, and now the surface roughness is lowest, which is type C. Now did you understand? Any other doubt you can ask?
Like if I get this right, ma'am, that means if it's A type, that means the band can propagate anywhere along the gauge length.
Yes,
If it's type B, then it can't like propagate all over the gauge length, but it can hop through the gauge length.
yes.
And while in C, it's basically not able to move only. It's the dislocations are
Yes.
due to the band.
Yes. So nucleation means the grain present in that leader band has been nucleated, and now the grain size is larger, so they can allow the dislocations anyhow to move further. So the propagation of the band is not occurring really. So it will be demolished after some time. This thing will be demolished after some time, and the surface roughness is not that much.
Also, ma'am, like when we're saying it's like a band, it's like just a collection of these dislocations and
Yeah.
okay, ma'am.
Band means a particular position where this Mg atom is creating this problem of DSL,
Okay, ma'am, got
or
it.
where the Mg atoms have found a preferable environment to create this DSL.
Okay, ma'am.
Okay, so yeah, this was up to lecture 3, and there were some things like mm, some points, few points or features of this serrated flow, which counts this types, then how the serration flow really looks like. This is one picture I have already shown. So this is how the serration flow looks like inside the aluminium. You'll see the aluminium graph like this always. So the next thing is lecture 4, the inverse behavior. So I have already discussed, when we are increasing the strain rate, we are supposed to get more stress, but here we are getting less stress. So this is the inverse behavior of the material. We are, yes,
I'm sorry to interrupt. Actually, I had a doubt in the previous points.
yes, please.
Actually, in that we had discussed this point, like DSA is basically related to how fast the dislocations are traveling, so that they can pin down, like, as solute atoms are traveling so that they can be pinned down. तो मैम like air में तो pinning जल्दी होती है तो shouldn't the DSA like happen earlier in that?
Can you please repeat the question? I didn't get.
DSA is basically how fast the solute atoms are traveling to pin down the dislocations. But in air alloys, basically this should happen faster at room temperature. So DSA should be there like a lot more.
Yeah, DSA is always present in the aluminium. This is what I have shown.
Uh,
Aluminium graphs always looks like this.
yeah, ma'am. But ma'am, like when we are saying strain rate and things like that, shouldn't it be higher than within that temperature range?
Uh, so what happens is this strain rate, uh, which is the strain rate range, is also not that much. It's only 10 to the power minus 5 to 10 to the power minus 2 per second. You can imagine per second we are increasing 10 to the power minus 2 percentage elongation. Means 0.001 by 100. So it's
Yeah,
very
it's
minimal. So this is why aluminum alloys always show serration. It already has a characteristics of showing serration in room temperature, and also the strain rate range for DSA is so less again. So obviously for aluminium it's a common phenomena. For steel it's a rare phenomena, because for steel it needs lot more strain rate and the temperature is also very high, to 25 or 300 something. So what is your question now?
like I was thinking that as the temperature increases, the solute atoms should be able to get enough energy so that they follow the dislocations faster. So in that case, like the stress between them should increase, no, like the
No, no.
strain rate.
What happens is when the strain rate is increased, na, the
Yes, ma'am.
solute atoms really cannot move because they don't get enough time to move.
Oh, acha, okay. So the
That
temperature
time the
depends.
solute atoms are only moving faster. The dislocations are not moving that much.
Okay, ma'am. Okay, I get
In
it. So
normal
this.
phenomena, you are absolutely right. For normal phenomena, you have understood, right, that for normal
Yeah.
phenomena, when we increase the temperature, the dislocations also start moving very faster, and the
Yes,
solute
ma'am.
atoms as well. So that is why the solute atoms cannot pin down the dislocation easily. But for
Okay,
DSA,
ma'am.
that is the reverse case. That is the negative strain rate sensitivity. That dislocations cannot find enough time to move. That is why the solute atoms get easily be seated in that position in front of the dislocation.
Okay, ma'am. Got it.
So yeah, if you have any other doubt, you can always ask. No problem.
No, ma'am, it's clear now.
Okay. So this is all about the serration flow or serrated flow. So as I have told you, the strain rate we are increasing and we are getting increased temperature, which results in the more solute atom movement and less stress. So this is the inverse behavior. Then the magnitude I have already shown, the magnitude of the serrated flow. So then there was a inverse graph between the sorry, strain rate and the stress. or the magnitude of the strain rate and the stress. Sorry, magnitude. And this is the strain curve. After some time, the serration will take place, and this is the magnitude. Magnitude will be high, and then it will start lowering down, because obviously when we cross that strain rate range, when we are beyond the strain rate range, the magnitude will be demolished after time, and there will be no serrated flow or DSA occurring further. Then adverse effect and the reduction in ductility. So can you tell me, so now till now I hope that you have understood the serrated flow and the DSA. So now can you tell me that why this DSA is resulting in decreased ductility?
Like ductility is basically the dislocations will be able to flow in that matrix easily, but DSA, the presence of DSA prevents that. So that's why ductility
Yes.
decreases.
So it's easy. Whenever you are talking in about ductility, always remember ductility means the dislocation movement. And if we are just restricting the dislocation movement, we are reducing the ductility. So DSA here we are saying we have learned that DSA is not good. We can restrict the DSA. We can avoid the DSA by many other means, but if we are trying to reduce the ductility somehow, DSA will help us. But again, DSA is not the solution, because we are not doing something due to which DSA occurs. It's like we are just increasing the strain rate, we are increasing the temperature, and we are getting the DSA. So DSA is not a continuous thing. It can happen, it cannot happen. It may happen, it may not happen. So this is why we can say, right, that if we simply can increase the strain rate and we can reduce the ductility, then while we are going for precipitation hardening, the different heat treatment processes. Now, DSA is so easy to reduce the ductility, but it's like DSA is easy to get, but DSA is not continuous. In type C, you could have seen that in type C, after sometimes the DSA will be demolished, and there will not be any serrated flow found further. So DSA is not a continuous thing, and it's not a permanent solution to get more hardness. It's just a phenomena. This is why we always try to avoid DSA, because somehow we are trying to reduce the ductility by precipitation hardening, by, or you can simply say, by some permanent solution. DSA cannot give us that permanent solution. DSA can only hamper the process we are going through, right? This is why we always try to prevent the DSA by just avoiding that strain rate range, or working in that particular temperature range. For aluminium, it's room temperature, so we cannot avoid. This is why we always get serrated flow in the stress strain curve. But for steel and other alloys, we try to avoid that temperature range to avoid the serrated flow. So this was all about all the lectures. Then the precipitation hardening started. So that was the first part of precipitation hardening. So I'll rather stop the DSA here, and we'll start the precipitation hardening from the next class, because it's completely a different phenomena. So in today's lecture, just try to understand the DSA only. So if it is done, then we can do another thing. I have some previous year problems, so I can just show them, and we can do the question answering.
Sure,
If
ma'am.
you have any, if you don't have any other doubt.
No, ma'am. I'll go through all this once again after this.
Okay, okay. So yeah, strengthening of aluminum alloys through elastic interaction is mainly due to what? Try to answer. Otherwise, we'll discuss.
Like formation of stacking faults, local change in shear modulus, and I think the third one is also there.
You just read the question again. Strengthening of aluminum alloy can take place or can be done in four ways, in which using elastic and interaction what mainly happens.
Okay, using elastic interaction, the first one, local change in shear modulus, and like the third one.
Yes, third one is right, but yeah, but shear modulus change was falling under the second segment, right? You can
Uh,
say the shear modulus is changing, but we have denoted it in, we have just made it in second or other segment, like the modulus interaction. So as of now, we can say we
okay,
can
ma'am.
pick the third option only, the compressive and the tensile field interaction.
Okay, ma'am.
Then in elastic interaction, strain field associated with substitutional solute atoms will interact with in elastic interaction.
Substitution, I think only go with one. Either, I'm not very certain, it's either screw or edge.
Yes, only one, it's H.
Yeah, ma'am.
Next is electrical interaction between solute atoms and dislocations arises due to.
Um, the last one, the solute of different valence act as the charge center.
So the solute of different valency act as the charge center and attracted by the dislocation force.
Yes, ma'am.
Then fourth, which is correct about stacking fault.
It's the second one. When the width is larger, then there's more resistance.
Yes.
Uh,
Okay, there is another one.
the
It's
last
right.
one.
And higher width of the stacking fault results in lower
Okay.
stacking fault energy.
Ma'am, once again, stacking fault energy is exactly what?
Okay, so higher resistance to the dislocation motion is due to the stacking fault width is more. So stacking fault width is more means the dislocations are, the distance between the dislocations are more. In stacking
Yeah,
fault,
ma'am.
what happens? A normal dislocation has been divided into two, and
Two,
in
yeah.
this middle portion the solute atom has been seated because they
Yes,
find
ma'am.
it the less energy fault. So when this
Okay.
happens or this is made, so in between these two dislocations, these are ordinary dislocations, these are not that much high length dislocations. So the in between place is always will have less energy. So due to that energy gradient, the solute atoms always sit in that position.
Yes, ma'am.
So this is why the stacking fault energy is lower with higher width, and formation of stacking fault in FCC, because ABC, if this
Yeah, ma'am.
B is cancelled out, so it will AC, which is like HCC. Next
Yes, ma'am.
is the stacking fault energy is,
It is directly proportional to the distance between the dislocations.
it's directly proportional to the separation between partial dislocations.
Um,
It's not. Directly proportional. One second. It was higher width of stacking faults was giving us the lower stacking fault energy. Obviously, the solute atom was B seated. But here it's saying directly proportional to the separation between partial dislocation. I need to check these things. Actually, I have uh, ge- got these things from the
Okay,
previous
ma'am.
year question answers only. So
Okay,
I
ma'am.
need to check this then. Okay, so as of now, it seems like only inversely proportional to the Berger vectors of the distribution.
Okay, ma'am.
Hmm. Uh, this should be the second option, inversely proportional to the separation between partial dislocation with or dislocation. So anyway, the sixth number, the alloying element is mainly responsible for yield point phenomena in aluminum alloys. Which one?
Magnesium.
Yeah, it was pretty good. Which of the following statement is or are correct in case of strain aging phenomena?
At upper yield point, the dislocation will be pinned down by the solute atoms, and due to strain aging, the yield point reappears at a lower stress.
Yes. No, for higher, not for lower stress. The
Uh,
yield point reappear at the higher stress.
uh,
But it's yeah, the lower yield point reappear. It should be like the yield point reappear at a higher stress, lower stress. Sorry.
yes, ma'am.
Okay, no problem. I'll recheck.
Okay, ma'am.
Again, I have just copy pasted it from previous year question answer.
Okay,
Uh,
ma'am.
Next is if the processing temperature of the alloy increases,
Ma'am, processing temperature, as in the temperature in which it is made.
which we are externally increasing.
Oh, okay. Then the mobility of the solute atom
Yes,
increases, and
yes,
the dislocation velocity also increases.
yes. So both the this is what question one question very important. So
Okay,
if we
ma'am.
are the processing temperature if it is increasing, so the mobility of the solute and the dislocation both are increasing. But in DSA, what happens is due to
Uh,
strain rate, higher strain rate, the temperature increases. There we are
okay.
not increasing the temperature. As I said now, for strain rate increases, as the strain rate increases, the temperature increases inside the material, which acts as a thermal activation for the solute atoms, and due to which the solute atom movements or mobility of the solute atoms increases. But for dislocations, they are supposed to be increased, the mobility of the dislocation, but as the strain rate is at very higher rate at the DSA range, the dislocations find it difficult to move because they could not find enough time to move. Because dislocation velocity, one thing, na dislocation should also have enough time to move through the lattice, and they are just not getting enough time to move. This is why
Yes, ma'am.
this DSA happens, which is different from the normal phenomena. This is why we always try to avoid DSA.
Okay, ma'am.
Next is region of disorder created by movement of dislocations in superlattice is called,
Antiphase
yes,
boundary.
yes. Last one is which of the following mechanisms is or are related to the solute solution hardening in the aluminum alloy. So it's from the previous week lectures, electrical interaction, then modulus
Yeah.
interaction, this two, and then that was the electrical interaction and the stacking fault.
Okay, ma'am. Yeah, I recollect.
Yeah. So there were only four ways of solute solution hardening. Yeah. So it's all about the previous year assignments.
Oh, ma'am, actually, I had a doubt in the last week's one of the questions we discussed about the hypoeutectic and hypoeutectic.
Okay, okay, please continue.
Ma'am, actually, there was a question in the assignment that was given regarding that last to last week, and in that we had selected the option of primary, like the phase that we got after, immediate cooling was primary silicon and alpha aluminum. Uh, I had thought of it earlier as well, and I selected that option, but they say it's wrong.
Which one is the right option?
Apparently, it's I don't remember exactly, but it was a very complex thing like eutectic silicon and alpha aluminum, a lot of things in it.
Okay, it's from week one question answer.
Week two.
Week two, current semester assignment.
Yes, ma'am.
Okay, week two current. I'll see and get back to you in the next class. Huh?
Sure, ma'am.
Week two current semester assignment. Hypoeutectic. So what we can do is, along with the previous year assignment of week 4, in the next class we'll also discuss about the current semester assignment of week 1 and 2, because the last due date to submit the assignment is already gone. So now we can
Yes, ma'am.
discuss about that thing, right? So
Yes,
yeah,
ma'am.
we'll discuss about it. And you had another doubt in last class, which is the problem regarding Cottrell Bilby theory. So the
Yeah,
normal
ma'am.
things also, this serrated flow, precipitation hardening for especially aluminum alloys and these things, you can't find it in anywhere in the normal Google search. These things are very critical, and if you are working with aluminum or if you want to know about these things, only then you go for this sort of lectures. So I also couldn't find any problem in Cottrell-Bilby theorem. I'll again find once. If I get, I'll show you. But as of now,
Okay,
I
ma'am.
didn't find anything.
Oh, no problem, ma'am. Thank you so much.
Okay. So the lecture 5. Okay. Another thing. So till now, I think we have covered all the lectures in week 3. Lecture 1, 2, 3, 4. If you still have any confusion, please clear it out today only. This is why I'm not going into the lecture 5 precipitation hardening, so that we can cover all the type of precipitation hardening in the next class. Or if you want, we can do today also.
Actually, ma'am, first lecture was clear for me for precipitation hardening. Like the problem started after that in the later on lectures.
Okay,
So,
week 4 lecture.
yes, ma'am. So, ma'am, I'll wait for it.
So okay, no problem. We can wait for it. There are natural aging, mechanism of hardening, artificial aging, the precipitation hardening, na, the TTT diagram, lattice
Ma'am, that
mismatch.
one.
Those are also very complex things. But this DSA was more complex. So this is done.
Yes, ma'am.
So yeah, we have 30 minutes left. So yeah, we can do one thing. I'll ask you some questions so that uh, I can see whether your concepts are clear now or not. Okay.
Okay, ma'am.
So what is the PLC effect, or what is the leader band?
It's like the effect I discussed about the formation of serrations. Basically, it says that in a particular temperature range and strain rate range, the aluminum alloys, the solute will try to catch up with the dislocations. And when the stress reaches a particular maximum value and okay, wherever there's a maxima and minima in the stress strain curve, there the strain rate will tend to infinity, which will cause a sort of a jump in the values for uh, the the stress and at the corresponding strain. So that'll cause like serrations to form. That leads to surface hardening. Sorry, some surface finish will be reduced because of that.
Yes, that is the leader band.
Yes, ma'am.
And the effect was described by this PLC, was called as PLC effect.
Yes, ma'am.
Okay, next is what is this thermal activation?
It's like thermal activation, and there is one more activation. Both of them are present when, like, I just kind of forgot that one.
No problem. It's like whenever, if we are trying to move somewhere, we need to
Yeah.
have a minimum number of minimum energy to move there. So for solute atoms or for dislocations, that is called the activation energy. For
Yeah.
dislocations, they need to overcome that activation barrier. So to
Okay, ma'am.
overcome the activation barrier, they need to have two types of energy, or they can have the activation energy, but we are defining or denoting the activation energy in two segments. The activation energy can be supplied through the applied stress, or that can be achieved through the thermal activation. So thermal activation is like hiding the temperature, and applied stress is like the applying cooling force we are giving. So it's the activation barrier energy, or activation energy to overcome the barrier for the dislocations.
Okay, ma'am. Understood.
Because anyhow the solute atoms will always be in need of some activation energy to find the nearby vacant place and jump into that. But for dislocations, they can easily move until unless they face any barrier. And the waiting time is the time they are waiting in front of the barrier, the time in which they are getting or acquiring that thermal activation and applied stress activation energy. That time is the waiting time. So the next
Yes,
is
ma'am.
the peening theory.
Yeah, ma'am. Like this, I think I explained peening theory for PLC theory.
Yes,
So,
that
like,
jump in the strain. So
yeah, the
one
jump
thing
in the stream.
to be remember is the strain rate. The strain rate can jump from one value to another value, where the stress cannot jump from one value to another value. Because you
Yes,
can imagine the stress is like the stress or interaction energy between the solute and the dislocations.
yes,
Neither
ma'am.
the dislocation can jump from one place to another place and until unless they get the energy, nor the solute atom can jump from one place to another place, so that there can be a jump in the stress value. So this is why the strain value can have a jump, which is here denoted in the loop, but the stress value is equal, and there is a mismatch in the practical and the theoretical value. This is why uh, this is where we are getting the strain rate sensitivity, which is coming out negative, which is giving us the DSA and the serrated flow. So there were some points
Yes, ma'am.
regarding serrated flow. So it occurs at particular strain rate and the temperature range. There were type A, type B, and type C serration. Also, always remember, if you are going for quenching, so there is one thing, loading, unloading, aging. This is normal phenomena. But for heat treatment processes, there are like heating and then cooling. So for heating, it's fine. We are just melting the material. But for cooling, the cooling depends upon, or the grain size depend upon the cooling rate. how we are cooling it. If we are cooling it in the furnace itself with a very slow cooling rate, if you are cooling it using quenching mechanisms, like we are just dipping the material in oil or water, so depending upon that, we get the different grain size. Now we are just understanding how the dislocations are moving and solute atom is seated over there. But when we'll understand the grains along with this dislocation and solute, you'll understand more. These things will be more clear to you, how the grain size matters so much to this dislocation movement and then this solute atom movement. As I have shown you, if you have a small length rubber band, we cannot pull out very much. The percentage elongation in the rubber band cannot be more. But if already the rubber band is having a more length than the previous one, we can pull out the rubber band more. We can have more percentage elongation, which happens in the grain size. If the grain size is smaller, we cannot pull the grains, or we cannot we cannot apply the tensile stress more, because the grains cannot be elongated more. But for the much more or bigger grain size, bigger grains, the grains can get elongated more. This is why the short or small grains result in more hardness than the long grains. Because dislocations means, yeah, dislocation is the lattice extra half plane somewhere using the following the screw path or the edge path. They're just moving along the lattice. When you'll see it in a boat, or a more or less magnified way, you'll see the grains. In grains, the grain following the grain boundaries, the dislocations move. So for dislocations is easily, they can easily move through the grain boundaries. And if the size of the grain is more, the elongation can be more. But if the size of the grain is so less, then the elongation cannot be more. So those are the different techniques by which we do the hardening. But DSA is not good for a material. We always try to avoid DSA, because suppose we are just trying to increase the hardness, but at that time we have come to the point where the temperature is falling in the DSA range. It will suddenly show some other variations and serration and serrated flow in the graph. It will hamper our working. We are just doing
Yes,
a
ma'am.
heat treatment, particular heat treatment, and suddenly the aluminum alloy or steel is showing us a completely different scenario. It will be a bad thing for us. It will not help us. So this is why we always try to avoid DSA, because at the end you can be asked, this question can be asked like, if DSA is reducing the ductility and DSA is giving us hardness, then why we are avoiding this DSA? DSA is good for us, because after at the end we are trying to increase the hardness, we are trying to reduce the ductility by aging, by heat treatment, precipitation hardening. So this is the reason, you can say. And then we talked about like the serrated flow is always associated with the negative strain rate sensitivity. Steel, aluminum alloys do have this type of serrations. In steel, the solute atoms are interstitial, as I have said. The carbon and nitrogen atoms sit in the interstitial position and increase the hardness. But for aluminum, the solutes are substitutional. This is why it's difficult for them to move and sit in the nearby vacant position. The diffusion rate is like how fast or slow the solute atoms are in moving and be seated in the next position. And diffusion rate is lower for the substitutional atoms always. Then we saw the graph of the sedation. So if the temperature is increased, the sedation will be observed at higher stress. So yeah, the stress will again increase, because if we are we you okay, you can answer me this question. So there was a graph like this. Wait, I'll draw. So there was a graph like, if this is the strain, this is the stress. We are having two graphs. This is T2 and T1, and T1 is less than T2. Then why we are getting these two graphs, and why this T2 is having more stress?
Ma'am, I didn't get it. Like, we are talking about the same alloy, but T1 and T2 are two different temperature ranges.
Yes.
Okay, ma'am. Like, I guess you're getting this because it's at two different strain rates. Like,
Mm, suppose this strain rate is fixed.
yes,
The
ma'am.
end point and the always remember, the end point and the starting point of this serration is fixed in terms of the strain rate. This
Okay,
is
yeah,
the
yeah,
lower
that's
strain rate and
onset
this is the
strain.
upper.
Okay, ma'am.
But the stress at which we are getting the strain rate is different for different temperature.
The onset stress is like different. Is it because of that?
Why? What is that onset?
Like it depends upon the temperature. Like I remember this was being talked about in the lecture.
What did you understand by this thing? You just think the way I have discussed to you, how the dislocation is moving, how the solid atom is
Uh,
behaving.
like if I think about it in that way, then basically once the when the solute atoms are moving and the dislocation is also moving, the temperature ranges are different. Then the rate at which the solute atoms will catch up with the dislocations would be better at a like in case, since this is DSA at a lower temperature. So like I feel that the onset of the stress would be a bit earlier.
Yes. So what happens is, when normally till this point there is no sedation, na? This is a normal phenomena.
Mhm. Yeah.
In this region, when we apply the external temperature, when we have increased the temperature, the solute atom and dislocations both will move faster. Even the
Yes, ma'am.
dislocation mobility will be even faster than solid atoms. So stress will be
Ma'am,
always
that
higher.
is, ma'am, this will be just after we have entered this sedation zone.
No, no. The dislocation mobility will be higher in this range, na? In this range.
Okay, yeah.
In this range, the dislocation movement is higher, mobility of the dislocation, than the solid atoms. But when they enter this region, it will be opposite. The dislocations will not get enough time to
Yes,
move,
ma'am.
and the solid atoms will always can always move, because they need to just find the vacancy and move. They
Yes,
will
ma'am.
move and be seated in front of the dislocations until this point. This is why, if we increase the temperature externally, this temperature has been increased externally. This temperature increase is not because of the increased strain rate. So if we have externally increased the temperature, always the stress will be increased. And whenever they uh, enter into the serration flow region, they will show serration, and beyond that also they will show the normal behavior, like the dislocations will just move faster than the solid atoms. Again, you can see here the stress is more than this point. This is 1 and 2.
Yes, ma'am.
This. So now it is clear.
Yeah, ma'am, it's clear now.
It's a normal phenomena for all over the path, for all the alloys, unless until they enter into the serration flow region, which is a particular range of temperature and a particular range of strain rate. You can also conclude from this graph that this T1 T2 doesn't fall under the range of the temperature or the serration flow temperature. right? This is why for T1, T2, we are having a normal graph in this region and in this region, in this region and in this region, right?
Okay, ma'am. So it's basically even though there are serrations, but since there is a normal portion also, that's why we're saying that it doesn't lie in that temperature.
Yes, yes. If the
Okay.
temperature was also falling in the serrated flow region, then all over the graph it was just opposite.
Okay, ma'am. Got it.
Yeah. So in serrated flow range of strain rate and temperature, the behavior of the graph will be opposite, will be something distorted like this. We know it will be opposite, like the strain stress decreases with increasing strain rate, but beyond that the behavior is normal. So that's why I told in the first half that you need to understand what is the normal aging, what is the normal loading unloading, then only you can understand what is DSA, because it's very important for you to distinguish between normal phenomena and the DSA phenomena to avoid
Yes, ma'am.
mistake, right? Okay, so this is why we are getting, so there is a critical, we are calling there is a critical strain or onset strain in which
Yes,
we
ma'am.
are getting that optimal or that what say that optimal serrated flow. We can say for serrated flow there is an optimal point of the strain rate which is called the critical strain. We are increasing the strain rate, but there should be a critical strain, means strain rate is like we have strain rate
Yes, ma'am.
1
I got it.
and
It's
we
like
have
dE
now we
by
are 2.
dt.
So the strain rate is 1 by second, 1 millimeter, 1 percentage per second. First the strain
Yes,
got
ma'am.
1 percentage, then 2%. There should be a critical strain at which or beyond which if we are increasing the rate of the strain rate will have the serrated flow. So that strain is called the critical strain, or you can say
Yes,
onset
ma'am.
strain. Okay, so at that point, solid atom will quickly catch up the distributions. Uh, then inverse relationship, DSA adversely affect the properties. So DSA just reduce the ductility, reduce the toughness. Fracture toughness is nothing but the toughness to reduce, to restrict the crack propagation inside the material or the fracture inside the material. There are different types of fractures and crack propagation which can occur inside the material. If you want we can discuss that also in one of our classes. That's another thing. Then so DSA basically reduces the fracture toughness and they hamper the part quality or the property of the material, inherent property of the material. So diffusivity of magnesium in aluminum alloy is higher at room temperature and at a particular strain rate, which gives us the sedation and the DSA. And magnesium is a
Yes,
must
ma'am.
have. Yes.
Yes, ma'am. Yeah.
Okay. So, and magnesium is a kind of must have alloying element. In all type of alloys of aluminium, you can find magnesium. This is why the 6000 series, 7000 series, all these series show sedation flow in the stress strain diagram. Mm, yeah. So this is about all till lecture 4. We'll discuss about the week 1 and 2. I'll write it down. Week 1 and
Sure, ma'am.
2 previous year. Previous year we have done, so current semester assignment, and week 4 previous year. Okay, so if you don't have any other doubt, we can stop our session today.
Yes, ma'am. Ma'am, actually, I wanted to ask you, where can I find the lectures, the recorded lectures?
You have not been shared this thing anything
Uh,
yet?
no, ma'am. I don't exactly know where I can find the content also.
Mm, okay.
Content as in the one that you used in the class.
Okay. Actually, this is not in my control. So I have uploaded the things. You are supposed to get the things soon. I think this thing will be shared to you through your Gmail, the mail you
No,
have
ma'am.
shared at the time of registration.
Oh, no, ma'am. I didn't get any email regarding this. Ma'am, do you know anyone I could contact for this?
Mm, I'll see. I'll tell you in the next class. I need to
Sure,
find
ma'am.
out. I'm also
Uh,
just a TA in this class, so I don't know
yeah.
those things.
Sure, ma'am. No problem.
Okay. Okay.
Thank you, ma'am.
Happy Independence Day. Thank you.
Wish you the same, ma'am.
Yeah. Good night. Bye.
Good night.